Okay, so this lecture corresponds to Chapter 12 of the Munsner text, and the great news is we're nearly done with the readings for the semester. So just a few more of these presentations and we'll be all wrapped up. So as usual, Munsner starts out her chapter with something called the big picture. The main idea here is to be able to show multiple views or facets of the same data, so you can look at multiple aspects of the information at the same time. This built on Chapter 11 that looked at view manipulation. In general, there are three different ways to facet information into multiple views. The first is to superimpose using layers. The second is to partition into multiple regions. And the third is to juxtapose the views to make them appear side by side. You can see all three of those in here. The juxtapose and coordinate multiple side by side views, partition into side by side views, and superimpose layers. So why facet? Well, facet is a verb meaning to split. Having multiple views at the same time is an alternative to switching views. And comparing two views simultaneously is often easier than flipping back and forth. And you know that if you have multiple monitors, you can compare two things at the same time or read off a set of notes rather than flipping back and forth between notes in a presentation, or comparing two graphs. You can have one in one monitor and one in the other. So it supports a better comparison, particularly if you can facet, or if you can facet it just into a single monitor, that works as well. So multiform design uses a different encoding in each view to show the same data, and small multiples involves partitioning the data between views. Sometimes we can choose superimpose since it does not require additional screen space. The cost of juxtaposed views is the space required. There's definitely a trade-off between the display area of the screen and the working memory of humans involved. And superimposition doesn't require more screen space, and we can change the view over time. However, it's often hard to create distinguishable layers. If you've done any work with layering, you can tell that it's kind of hard to get those layers so that they can be distinguished from one another. So for juxtaposing and coordinating views, we need to consider how to link the views, particularly for juxtaposition. Most common method for linking views is shared encoding views. That means they all have the same channels. That is, their color, size, etc. are the same for the marks. You can also have multiple form views. This means that some, but not necessarily all of the views are going to have the same encoding for their marks. This is good since a single monolithic view has limits on the number of attributes that can be highlighted. So each view could focus on its own attribute for encoding. So let's take a look at an example. And this one comes from Major League Baseball. And I know that a lot of the students in this year's class are into basketball, but forgive me, we're going to do a little bit of baseball. And basically here, what we're looking at is putouts and salaries, assists, and hits per year by position. So according to Major League Baseball, a fielder is credited with a putout when he's a fielder who physically records the act of completing out. So that could be stepping on the base for a force out, tagging a runner, catching a batted ball, or catching a third strike. A fielder can also receive a putout when he is the fielder deemed by the official score to be closest to a runner called out for interference. Catchers record putouts by catching pitches that result in strikeouts, and first basemen who record putouts by catching throws on ground ball outs generally amass the highest putout totals. So when you look at the players with high salaries, the hits correlate with salary, but not putouts. And again, that's because, the first baseman and the catcher are going to be the two that get the most putouts. And while good catcher is worth a lot of money, first baseman, you can typically pick up a really good first baseman who will record a lot of putouts. It's not a necessarily the hardest fielding position there is. So if you look at part A, then it shows players with high salaries, and the hits are correlated with the high salaries. If you select B, the putouts, then it shows a coordination between the putouts and the position. So second design choice is how much data to share between the views. And there are three options. Number one, both views can show all the data with overview to detail. One view can show a subset of what is in the other. And third, the views can show different partitions of the data set into disjoint pieces. That's the small multiple. So for an example of overview to detail, that's the most common way of sharing data on a map. So if you look in the lower right-hand corner, you can see the bird's eye view of the map. And you can see that we're looking at kind of the boundary between Washington State and the province of British Columbia in terms of the detail. The detail takes up the rest of the screen, but that overview is in the lower right. And so that's an example of faceting. We're kind of looking at the same place, but we're looking at the details in the main screen and looking at the overview in the lower right-hand portion of it. So a bird's eye view is a view from a high angle. This is, what a bird might see in flight. Of course, I think it'd have to be flying pretty high to, see two states and multiple states and a couple of different provinces. I think Alberta is kind of over in the far right of that bird's eye view, but basically it's how a bird would observe something in terms of its definition. This is an example of a multiform overview with detail. In this figure, you can see the coordination between the scatter plot that's in the center of the graph and the view in the upper left. So you can see the view in the graph view for the time period specification. And then when you zoom in on that or narrow it down, you can see the actual scatter plot of that data. And 4/5 of the tasks here are export-based, are consume-based tasks, while export is a production action. And so you can see different views that correspond with different tasks. And unlike the overview detailed, the information displayed is different for each facet that we might be looking at. For example, if we change the range sliders, that corresponds to a different task, or if we look at the gene list, that corresponds to a different task. Small multiples is another technique for faceting, and these are multiple views with the same encoding and different partitions. The shared visual encoding means that the views have a common reference frame, so the comparison of spatial position between them is directly meaningful. Small multiples are often aligned into a list or a matrix to support different comparison with the highest precision. The encoding is identical, but the data differs. The strength of this approach is that multiple views are available side by side. The drawback is that it takes a lot of screen real estate. This is from a system called Cerebral that you see here. Here we see the same base graph of gene interactions colored according to microarray measurements made at different times. And you can see both the network data and the scatter plots. And the problem, if you were looking at the bullet point, was that all subplots are red-green. Complex systems will often use different methods. And so here we have census data that uses many different views. In addition to the geographic information that we kind of see in the center left, the demographic information for each county includes population density, genders, median age, percentage change since 1990, and proportions of major ethnic groups. So there are different multiple facets of different types that ensure coding and links. So when you highlight one thing, it changes the other codings. Partitioning the views, so partitioning is an action on a data set that separates the data into groups. The design choices involves how to divide views given a hierarchy of attributes. So some considerations are how many splits to carry out and the order in which the attributes are used. They make use of glyphs, which is an object with an internal structure that arises from multiple marks. And you can have a recursive subdivision to allow regions to nest inside one another. That's another important thing with partitioning. And the term glyph here is somewhat ambiguous in visualization literature. And I'm using Munzner's definition when I say it's an object with internal structure that arises from multiple marks. Merriam-Webster gives a slightly different definition. A glyph is a hieroglyphic character or symbol, a pictograph. And in computers, it's often defined as a small graphic symbol. So here's an example, a single bar chart with grouped bars separated by state into region using 7 glyph marks within each region. 4 line small multiple bar chart views separated by group key into vertically aligned list of regions with the full bar chart for each region. So again, we're taking that overview and then we can see the details in part B. This is a fairly well-known data science example on barley growth. This is from the Morris panel. This chart above shows yields for several different varieties of barley planted at each of 6 different sites in Minnesota in the years 1931, 1932. The reason this data set has become legendary appears in the Morris panel, where unlike all the other sites, the yields in 1931 exceeded those in 1932. This is a great demonstration of the power of dot plots and panel graphics. In his book, Cleveland said that it's either an extraordinary natural event, such as a disease or a local weather anomaly produced by a strange coincidence, or the years for Morris were inadvertently reversed. And on the basis of evidence, the mistake hypothesis would appear to be more likely to be correct. But now it looks like, despite Cleveland's suggestion, the data are correct after all. In a paper in the American Statistician published a couple of years ago, Kevin Wright notes that in the time period, local effects of weather, especially drought, insects, and disease, had a greater impact on barley yields than any overall year-to-year effects on yields, and that the results at Morris were not surprising. If you're pretty eagle-eyed on this slide, you can see the Morris site, and it's kind of located in the center there. And you can see 1932 was higher for the Morris site, where it was lower for all the other ones. And so you can notice that the Morris site goes the opposite way of every other piece of data. Color makes it easier to see what's happening. You can see the Morris site here. When you color it, you can see that it goes the opposite way of everything else. The pink dots are on the right in every other plot except Morris, where the blues are on the right. You also have the option of superimposing layers in terms of faceting by combining or stacking them on top of one another. So how many layers, are some of them static or some of them dynamic, and how to partition layers are design choices you should consider. The most common example of this is cartographic layering, where layer 1 might be the water, land, and parks. Layer 2, we could add the roads, and layer 3, we could add the cities. You can also do the same thing with line charts, but this gets kind of messy, and it doesn't scale well beyond a few items. When we're looking at a lot of items, we want to think about how do we reduce those items, or how do we reduce those attributes, and that's what we're going to talk about next week. So thanks so much for watching, and we're nearly at the end here. Thanks again.